Hi, I'm Eamon Walker, a PhD student in mechanical engineering at Louisiana State University. As part of LSU's IGERT program on multiscale computational fluid dynamics, I'm working on numerical simulations of multiphase flows in microchannels, specifically for bioanalytical lab-on-a-chip applications. Now, a lab-on-a-chip is a device used to run chemical analyses for various applications, such as discovering new drugs or running blood tests in the field. But by performing the tests on the microscale, we can drastically reduce the required sample sizes and increase the testing rate. Basically, instead of running a test manually in the lab, the testing samples are pumped through tiny channels running through a glass or polymer chip. And the chip is designed so that processes such as mixing and sensing are performed automatically. Now, one technique of increasing interest is to generate segmented or multiphase flows inside the channel. Basically, if we inject what we call a carrier fluid into the flow, we can break the sample fluid up into separate capsules or droplets. Each droplet now houses its own set of chemical reactions, and the localized mixing and almost zero dispersion of particles can often provide improved test results. Meanwhile, the carrier fluid creates a buffer which prevents the absorption of proteins or other molecules onto the channel walls. By adjusting the flow rates of the two fluids, we can achieve different types of flows in the chip. Now these flows, specifically segmented flows in rectangular microchannels, while they have a lot of potential, very little research has been done on them so far. So what I do is to run numerical simulations of these flows in order to alleviate some of the mystery behind them. I have a parallel Fortran research code that I run on the Lonnie supercomputing network to simulate hundreds of specific flow scenarios. Then we look at things like the droplet shape or the pressure drop along the channel and map the relations between these parameters and the characteristic values of the flow. And because the flows are simulated numerically, we can go in and visualize things like the pressure field and velocity field to try to physically explain certain trends that we see. Now, the other side of the project is to evaluate the code and try to improve it if possible. For example, I've worked extensively with the Applied Maths and Modeling department here at the University of Lyon, and together we have applied a method called Schwartz-Adkin acceleration to the code to see if we can make it run faster. Now we also have cases we want to run where the carrier fluid separating the droplet from the walls becomes too thin for the code to be able to resolve it. So I'm working on implementing an algorithm based on lubrication theory in the code, which would allow us to simulate these flows. Well, that's a brief overview of my project. Thank you for taking the time to watch my video. And if you'd like more detailed information on my research, please check out my poster in the link provided. Bye.